Good day everyone. In the previous video, using the trial and error method, we showed a simple PID angular speed control design for a hobby brush DC motor. The motor we used had no load on it, and this is still the case in this video. Suppose now you would like to analyze the performance of this specific DC motor and driver in Matlab in order perhaps to analyze the open loop performance or the closed loop performance, or to find the PID parameters in Matlab. In order to do this, you need to find the transfer function for both the driver and the motor. When it comes to the motor, there are multiple options you could use in order to estimate the transfer function. You could perhaps check the datasheet in order to find the physical parameters of your system, or perhaps you could measure those parameters and when we're talking about parameters, normally we are referring to the armature resistor, armature inductance, torque constant, back EMF, viscous friction, rotor moment of inertia, etc. Now the third option you could have, you could assume that your motor is a black box and analyze the step response by finding your gain or tau in case of first order system. In case of second order systems, you could use your maybe overshoot percentage to find the zeta, and then you could use the damped frequency in order to find the natural frequency. There are many equations available for you, and you will be able to estimate the transfer function. And that the same applies if you use as well the frequency response. If you can obtain the body plot by inputting a sinusoidal waves and measuring the amplitude variation of the output in terms of the signal strength, or if you can measure the phase lag as well, you will be able to establish the frequency response, and from there as well you could find the parameters needed, such as the gain or the cutoff frequency, and you will be able to estimate the transfer function accordingly. When it comes to the first option, it's not always you will be able to find a datasheet for your plant. Your plant could be more complicated than just a motor. Even for motors available in the market, especially for the hobbyist DC motor, you may not find a lot of information about those motors in terms of the parameters we discussed before. For example, if we go to the datasheet of a similar hobby DC motor used, you won't find a lot of information about it. You may find a maximum RPM, you may find some gearing ratio, but you won't be able to find the back EMF, the inertia, or maybe the viscous friction, or the torque constant, etc. Going to the second option, measuring parameters, this could be a little bit a tedious task. The third option is most of engineers using the or assuming the motor as a black box, and you can analyze the step response of it or the frequency response. In our work today in this video, we will base our method on number 3, but we're going to be using the system in Matlab, assuming it's as a black box, and we're going to be using the System Identification Toolbox. So in this video we will show you the procedure of how we estimate roughly the transfer function for both the motor and the driver. To do this, we will assume both are as a black box, and we shall put various inputs. So for example, we may start with square wave, and then we should see how the motor is responding. And from such information, we would be able to find the relation between the output and the input. It's worth also noting that we will assume that this motor and the driver are both time invariant systems. What does that mean is that the output does not depend on when the input was applied. Also, the errors of the parameters identification, nonlinearities, or the temperature influence are all ignored in this experiment. And talking about nonlinearities, you could check if your system is nonlinear by simply, you could, for example, double your input and so on, and you can check whether the output doubles as well or not. If it doubles with the same amount, then we could just assume roughly it's linear. Of course, you need more data inputs to verify, but that's the idea. Before we move on to Matlab and find out the estimate the transfer function here, we could maybe check for linearity of the system. So perhaps we could use a 200 RPM here as a maximum value, and we could use the initial one as 100, because I know that motor could saturate at 300 roughly. So 100 to 200 is roughly within the operation range for this motor. So running the Arduino code such that the Arduino will be outputting a PWM wave in order to mimic the blue profile. So the encoder for the motor should be responding to the profile shown in blue. And let's see the performance. Turning on the power supply, so the blue line is the user input and the red profile is the motor response. Now these values is around 170 approximately. So the motor is responding in 170 to 100 input RPM. Now re-downloading the Arduino code with a square wave peaking at 200 RPM to mimic the profile shown here in green, we will see how the motor will respond. Turning on the power supply now. Turning on the serial plotter. You can see that the blue line again is the user input of a value of 200 RPM, and you can see that the motor is responding in a value about 290. But perhaps that's reaching the saturation. It seems at a value of 200 RPM, the motor responded reaching almost the 300 RPM, which is the saturation number. So I will modify this. I'll tune it to 150 RPM instead and repeat the experiment. So repeating the last attempt by reducing the square wave amplitude to 150 instead of 200 in order to avoid the motor reaching the saturation region. downloading the Arduino code and turning on the power supply, serial plotter, so the red line is peaking at about, let's turn on the serial monitor, so it's around 230, so it's peaking around 230. So in the previous attempt at 100 RPM we had around 170. At 150 we are getting around 230. So doing the quick math, in the second attempt we are getting the peak here at around 230 RPM, whereas here we are getting our about 170. So doing the quick math, here we are multiplying by 1.5, and 170 multiplied by 1.5, that's gonna give us around 260 or 255. So we should have got around this value instead of 230. This dictates that the system is not linear, but it's not too bad. We will, of course, we should have tested this with more inputs, but that's not the objective of this video. The objective of this video is just to show you how you estimate your transfer function. But we had to do the nonlinearity test because estimating a linear transfer function is not the same as estimating a nonlinear transfer function. We will assume that this transfer function is linear, and we will carry on in the Matlab estimation process. Okay, now we have our system kind of quasi-linear, or we assumed it to be linear. We could go to the Matlab using the System Identification Toolbox in order to estimate the linear transfer function. However, in reality, you should have much more inputs in order to capture all the dynamics of your system or plant. For example, you could have a multiple sawtooth input signals with variable periods, or even you could have a sinusoids with a variety of frequencies, or perhaps you could have some sort of a varying square waves where you can capture more information about your system, and so on. In Matlab you can even estimate your transfer function based on a merged bunch of inputs. Let's go now to Matlab and find out how we're going to estimate our linear model from these two inputs. But before doing so, we have saved those outputs in Excel. So you could either copy paste them from your serial monitor to Excel if you only have one data set, or you could use just the PLX DAC software where you can send your data from the serial monitor straight away to your Excel, or you could use Data Streamer. This is also an add-on in Excel, or alternatively simply let Simulink do the job for you in Matlab. In order to use Simulink, you have to download the Simulink support package for Arduino hardware, where you can simply upload a Simulink block diagram directly to your Arduino, where we'll be able to communicate with your inputs. So it will stream your data straight away to Matlab workspace environment. You could later change those into an ID data where it can be straightforward or directly used by the System Identification Toolbox. My data look like this. There are two columns. The first column is my input, which is shown in blue here, and the second column is my data. So let's import these into Matlab. So let's now import the Excel data into the workspace. You could call your Excel file a variable here. In my case, I called the first file as A, and you will notice that this was created here in the workspace. I'm going to call the first input column as U1, so the first column of A is called U1, and I'm going to call the second, or the output, as Y1. This is kind of in line with your control system. Normally we call the U as input, Y as an output. Now the U1 and Y1 are the first and the second column respectively of file A. We will repeat the same procedure for the second file, which was run at 150 RPM. This file is 100 RPM, square wave. We call this one B, and also the first column we call it as U2, and the second column as Y2. Now we have all the needed information here in the workspace. We can simply start the System Identification Toolbox. So you need to install the System Identification Toolbox, and after you do this, you simply type the System Identification. Okay, you will get the window. The first thing we need to do is to import the data. We could just simply now import one set of data and get the transfer function for it, and then we can validate it against the second data. Cross-compare it to see whether the obtained model really represent the other set of data. To do this, you go to the Import Data drop-down menu, go to the time domain. You will be prompted to enter the workspace variable. Now our workspace variables are here. So first we need to perhaps grab the let's grab the 150 RPM. So let's grab, for example, U2 and Y2. The output is Y2. That's the open loop DC motor. Starting time from 0. Sampling time, let's just give it a 50 millisecond. We just hit import. Let's close that one for a minute. This is the data. If you're not sure which data you imported, or you want to verify it, just hit the time plot. If you remember, this is the square wave with an input of 150, and if you remember, the output was in the 230 RPM region. So that's the output, which is Y1, U1. Alright, so we are satisfied that these are our data. Of course, you could even analyze it in terms of frequency. You can tell that the performance in terms of a low frequency to the higher frequency. But let's now find the transfer function for this model. You can, if you have multiple data sets here, you could just simply drag yours into the working data, which is already been moved on automatically since we have only one set. You go to the estimate transfer function. Now you will be prompted to put the number of poles and zeros. From the previous video, we showed you that the motor transfer function is second order. However, it can be also estimated to a first order. But let's leave it with the 2 poles and 1 zero for now. You could either choose continuous time transfer function or the discrete. We will keep our plant in the continuous domain because that's what normally is in real application. So we're just going to say estimate. What you will notice that the estimate was completed and is successful, and it resembles the original data 97% validity. So that means if we close that one, this is the estimated response based on the model. If you just click on it, this is your transfer function. So you can use this transfer function to resemble your motor driver and the motor itself. You could take that model into Matlab. You can analyze an open loop, closed loop, find your PID parameters, same as we've done in our previous videos. That's it for what I need to achieve in this video. But we can go further by validating the model we just worked out against the set of data we obtained at 100 RPM as an input. So let's import the other data set. So we're gonna grab this data into the validation data. And what we're gonna do now, we're gonna simply click on the model output. If you click on the model you have estimated, you will find that when you compare the model you calculated against the data you obtained in the second set, you will see there is a 94.5% fit. If you look in the black wiggly lines is actually your measured data, and if you use the model we just worked out, or more 94.5% representing the measured data. There are a lot of options in the System Identification Toolbox that you can go over and learn. And if you wanted to estimate it as well in the Z domain, that's also done by simply by a click of a button. So double clicking on this, that's your discrete time domain transfer function. You could also estimate this in a continuous domain but with a first order. So for example, you can just go, you can grab your data and move it to the working one. I don't mind whatever set I have here because they're almost the same. We could just simply now choose maybe 1 pole and no zeros. Okay, so we should put maybe 0 there. So you will notice that it's 97% as well, representing the data using the first order. Let's find out how it looks like. Double click on your new model, and oh, we haven't put the 0 for the 0, so let's go back. Let's delete this one. Let's re-estimate it with no zeros in the numerator. So we're gonna put 1 pole and 0 for the zeros, and let's estimate. Now this is on 97.6, which is the same as before, still good. Now double clicking on our new estimated transfer function, this number seems to be what you would be expecting if you have to resemble your transfer function with the first order. Okay, in this video we just showed you how to estimate a kind of a linear transfer function for your motor driver and a hobby DC motor combined together using the Matlab System Identification Toolbox. We assume that the motor and the driver is a black box. We injected the black box by a certain input, and we recorded the output. From the relation of the output and input, Matlab assisted us in estimating the transfer function. Now, of course, based on the type of the input, you may predict if your system is linear or nonlinear. For nonlinear cases, you have to have as many inputs as possible in order to capture the full dynamics of your system, and you can merge the inputs in Matlab, and you can estimate your nonlinear transfer function this way. Okay, that's it for this video. Thank you for watching.